Good morning, students.
Asif sir,
Morning, sir.
sir, good morning. స్టార్ట్ చేస్తారా సార్? 250 ఉన్నారు.
Start చేస్తాం. Chalo. Come to next chapter, beta. Nuclear physics and radioactivity. Nuclear physics and radioactivity. So first one, let us try to talk about nucleus, beta. So what is a nucleus, beta? You know that every atom at its center is extremely very dense, which is what nature, beta? Positively nature. That is the reason when alpha ray scattering experiment was being going on, when the rays were being incident, among the 10,000, only one ray was being reflected. So when it was being reflected, they could able to confirm that there was at the center of the nucleus, there is certain thing which is having a nature of positive, that they defined it as a pure nucleus. And you know that every atom, whenever you talk about at its center, there is an extremely very dense and positively charged nucleus, which is much smaller than the overall size of the atom, but contains most of its total mass. Atom యొక్క total mass అనేది towards the nucleus ఉంటుంది. So what is a nucleus, beta? Nucleus is nothing but of your what? A positively charged part or extremely dense particle, like you can say basically. So I can say that every atom contains at its centers at its center an extremely dense an extremely dense positively charged nucleus. Positively charged nucleus. Okay, which is much smaller, than the overall size than the overall size of the atom. Overall size of the atom, but contains most of its total mass. Most of its total mass. So every atom contains at its center an extremely dense positively charged nucleus, which is much smaller than the overall size of the atom, but contains most of its total mass. Your total mass. That is called as of your nucleus partition. Now, what is the nucleus contains, beta? Nucleus contains your protons and as well as of your neutrons. Protons and neutrons are collectively or called as of what? Nucleons, beta. Nucleons means either proton or either neutron part of a nucleus. So I can say that nucleus is equals to protons plus neutrons. Protons and neutrons. Protons and neutrons are collectively known as nucleons. Or collectively are known as nucleons. Nucleons means it is either proton or nucleon. Nucleons means either proton or neutron. Either proton or neutron partition. So what is the nucleus, beta? Nucleus is nothing but what? Nucleus is nothing but of your process of your, it consists of both protons and as well as of your neutrons partition part. Okay. Already me telsinde. Then tell me what is the mass of your proton, beta? Mass of your proton is equals to 1.6 into 10 to the power of minus 27 kg. Mass of your neutron is equals to 1.6, approximately same, beta, almost all same partition. So it is approximately equal to 1.6 into 10 to the power of minus 27 kg. Isn't it? The 231 unte, it might be some 286 something right now. So, but almost all both of them are same part of relation. So 2 digit వరకు తీసుకుంటే మాత్రం 1.67 ఇది కూడా రాసుకోవచ్చు. దీన్ని కూడా 1.67 అని రాసుకోవచ్చు. 1.67 into 10 to the power of minus 27 kg. Mass of neutron is also that much. And mass of your proton is equals to 184 times of your 1840 times of mass of electron. Mass of your electron particle relations. This is also one of the important relation you need to remember. Okay. The next one is atomic mass unit. Atomic mass unit. Atomic mass unit. AMU. AMU. Atomic mass unit. So unit which is used in describing the mass in the nuclear masses is called your AMU, beta. Unit describing the masses in the nuclear physics is represented by your atomic mass unit, beta. One AMU is equals to how much, beta? Already you know in the chemistry. One AMU is 1/12 of the mass of your neutral carbon atom in its lowest energy state, which contains 6 protons, 6 neutrons, and 6 electrons part of relation. So I can write that point right now here. Symbol is your AMU. Sorry, it is your AMU, small a to round. So no problem. Just represent that one. Symbol is AMU. Symbol is AMU. Okay. So AMU is represented by the symbol U, small u. It is represented by your small u. So I can say that AMU is 1/12 of the mass of a neutral carbon atom. neutral carbon atom in its lowest energy, in its lowest energy state, which contains, six protons, six neutrons, and six electrons. Okay, one atomic mass unit, 1U, is equals to 1.66 into 10 to the power of minus 27 kg. One atomic mass unit is equals to 1.66 into 10 to the power of minus 27 kg part of a relation. Clear? The composition of a nucleus can be described by some terms beta, which you already know it basically. So Z is the number of atoms. Z represents me what beta? Z is nothing but of your atomic number. Z is your atomic number. Atomic number means nothing but what? Number of protons. Number of your protons. The same way N. N is nothing but what? Neutron number. This is nothing but of your neutron number. That is equals to number of neutrons. That is nothing but a number of your neutrons. And the same way A. A is nothing but of your mass number. A is nothing but of your mass number. That is equals to Z plus of your N. Z plus N. That is total number of protons and neutrons. This is nothing but of your total number of protons, total number of your protons and neutrons. Total number of your protons and as well as of your neutrons. Okay, so symbolically we represent it is a nucleus is represented by X, Z, A. Okay, in which X is the chemical symbol of the element beta. X is nothing but what? Chemical symbol of element. A is your mass number. Z is your atomic number part of a relation. Okay, na? Like example, if I am writing uranium 92 to 35. It represents me what beta? Uranium nucleus. It represents your uranium nucleus. So which contains 92 protons and 143 neutrons part of relation. So how many protons beta? So 92 protons and 143 neutrons. Ante kada? So this A is nothing but how much for me? 235. So it is 235 is equals to Z value is nothing but how much for me? Atomic number 92 plus number of your neutrons kavala. That is nothing but of your N. So this will give me 143. Okay, na? Let us try to define what do you mean by isotopes. What do you mean by isotopes, beta? Anyone? The nuclei which are having the same number of protons but different number of your neutrons. The nuclei having same number of protons, same number of protons, but different number of neutrons, neutrons. Example C611, C612, C613, C614. Same way 1H1, 1H2, same way 1H3. Hydrogen, deuterium, tritium, go on like that. So what are the isotopes? The nuclei having the same number of your protons but different number of your neutrons is called as of your isotopes. The next one is isotones. Isotones. What do you mean by your isotones? Isotones means it has the same number of neutrons but different number of your protons part of a relation. So I can say that the nuclei having same number of neutrons, but different number of protons, different number of your protons. Example C614, Wo8, 16 oxygen, fluorine 9, atomic number 9, mass number 17. So number of your neutrons same unnayalo chudandi sir. So it is 14 is equals to 9 plus 6, 14 is equals to 6 plus n. So n value will be equal to same for all the given conditions. It has the same number of your neutrons but different number of your protons part of relation. The same way next one is isobars. Isobars. So what do you mean by isobars, beta? The nuclei which are having the same value of your mass number. The nuclei having same value of mass number. Okay, the nuclei having the same value of your mass number is known as of your isobars. Mass number, how do you represent, beta? Mass number is represented by your capital A. Example student, C616, and nitrogen 716, oxygen 816, fluorine 916. They're having the same value of your mass number but different atomic numbers. They are called as of your isobars part of relation. The next one is nuclide. Nuclei. What do you mean by nuclei, beta? All the nuclei with a given Z and N, ante mass number and the number of neutrons, are collectively or called as of your nuclide part of relation. All nuclei with a given atomic number and neutrons, capital N, are collectively called a nuclide. So thus all the aluminum 1327 nuclei taken together is one nucleate part of relation. So I can say here right now, all the aluminum like 13, and this one is mass number 27 nuclei taken together taken together is one nucleide. Okay. So these are some of the terminologies which you should remember in the given condition part of relation. So these all things are the basics which you know it from the very starting. So I'm not giving much stress on this one basically. So let us try to go for the next one. Radius of nucleus. Radius of nucleus. Okay. Radius of your nucleus. So radius of nucleus is nothing but beta. So if I'm assuming the nucleus as a sphere, okay, then its radius capital R will depend upon the mass number, isn't it? You know, generally nucleus is not exactly in the spherical, but if you are assuming nucleus as a sphere, its radius capital R, depends on mass number capital A. Radius depends on the mass number capital A. See here, R is directly proportional to A to the power of 1 by 3, experimental value beta. Removing the proportional constant, R is equals to R naught A to the power of 1 by 3, where R naught is a constant beta. Value of your R naught is 1.2 into 10 to the power of minus 15 meters. That is equals to 1.2 Fermi meter. Okay, so this is your radius R. R is equals to your R naught A to the power of 1 by 3, where R naught is 1.2 Fermi. 1 Fermi is 10 to the power of minus 15 meters per definition. The same way, nuclear density. Nuclear density. So what do you mean by nuclear density? Density is equals to, you know already the formula. Density is equals to your mass by your volume. Okay, so let's say let mass of proton is almost all equal to mass of neutron, that is equals to your m అనుకుందాం. ఎందుకంటే both of them are right now in the nucleus. So mass of proton and mass of neutron, I am representing it by your n. Then density can be written as density is equals to total mass by total volume. Total mass is nothing but of your m into your a divided by volume is 4 by 3 pi into your capital R cube. So if I'm simplifying this one right now, R value already I know. So density rho is equals to your m into your a divided by 4 by 3 pi into R is equals to how much for me? R naught into your a to the power of your 1 by 3. Antena? So R value is equals to how much for me? R naught. R naught is equals to your R naught a to the power of 1 by 3. ఇది మొత్తం మళ్ళా whole cube. That means this a will get cancelled right now here beta. This a and this a will get cancelled. So density will be equal to your mass divided by 4 by 3 pi into your R naught. Okay, that means density is independent of your what beta? Mass number. It is independent of your capital A. Capital A is nothing but what beta? Mass number part of relation. So this is the important relation you need to remember. So density is equals to your m by this one, and I can say that rho is, so density is enana?
R not cube.
Sorry, this one is R naught cube. This one is your R naught cube part of relation. So density is independent of what beta? Mass number capital E. Okay. So that was the sum of the basics you should have been known in your nuclear physics beta. In this one, numericals general ga vachedi maatramu first numerical vachesi r is equals to r naught a to the power of your 1 by t part of relation. And density kuda rasetappudu itte rastamu. Sometimes even beta mass ivvakapothe we can conserve it from the momentum. Like say m1 v1 will be equal to your m2 into v2. So I can write from this one m1 by your m2 will be equal to your v2 by your v1. Okay, velocities gonna stay. This one are nothing but what beta? Velocities, momentum conservation. Okay. Next one is nuclear spin. Nuclear spin. See, the protons and neutrons which have been present inside the nucleus, they will be moving in a well-defined quantum states better. It is not like a random conditions. Okay, and they will be having the orbital angular momentum. So the protons and neutrons also have an internal spin of your angular momentum, and proton and neutron overall is also having the momentum. That means the total angular momentum of a nucleus is the resultant of all the spin and as well as of your angular momentum of individual nucleons. Okay now, so I can say that right now the total angular momentum of any nucleus, so I can write the point right now, the protons and the neutrons, the protons and neutrons inside a nucleus, inside a nucleus move in a well-defined quantum states, well-defined quantum states, and they have orbital angular momenta, and they have orbital angular momenta. Okay, that means the protons and neutrons also have an internal spin beta. The protons and neutrons, whatever we are taking, the protons and neutrons, the protons and neutrons also have internal spin, also have your internal spin angular momentum. Okay, that means the total angular momentum of the nucleus is what beta? Resultant of all the spin and also the orbital angular momentum of individual nucleons. That means the total angular momentum of a nucleus is called as of a nuclear spin of that nucleus part of a relation. Okay, so I can say that the total angular momentum, the total angular momentum. What do you mean by angular momentum beta? L is equals to I into omega. The total angular momentum of the nucleus is the resultant of all the spin and orbital angular momenta of individual nucleus, of your individual nucleons. So the total angular momentum of nucleus is called as what beta? The total angular momentum The total angular momentum of a nucleus is called nuclear spin of that particular nucleus. Okay, so కొంచెం theoretical questions కోసం important అయినా. So nuclear spin is nothing but what beta? The protons and neutrons inside a nucleus will move in a well-defined quantum states, and they have an orbital angular momentum. So the protons and neutrons also have an internal spin of your angular momentum beta. So this internal spin and the angular momentum spin, the total angular momentum of the nucleus is the resultant of what beta? All the spins and all the angular momentum of the individual nucleons. That means the total angular momentum of a nucleus is called as what beta? Nuclear spin of that nucleus part of a relation. Clear for everyone? Okay now? Sure. Next one is mass energy and nuclear bindings. Mass energy and nuclear binding energy and a nuclear binding energy. Mass energy and your nuclear binding energy. So let us try to talk about first one is mass and energy relation. Einstein's mass energy equation. Relation between mass and as well as of your energy. See, according to the Einstein, mass is another form of energy beta, and it can be converted to mass to energy and energy to your mass or into some other forms of your energy like kinetic and vice versa. So that energy is given by the formula by a relation called as mass energy equivalence relation. E is equals to m into your c square part of relation. So I can write here, according to Einstein, according to your Einstein, the mass is other form of energy, is an other form of energy, and one can convert mass to your energy, into other forms of energy, like kinetic energy, so on, anything. So that energy is given by the relation E is equals to m into c square. It may be kinetic energy, potential energy, electrical energy, magnetic energy, isn't it? Nuclear energy, gravitational energy part of relation. So it's form of another part of relation. So E is equals to your m into c square is nothing but of your energy and mass equivalence, where C value is equals to 3 into 10 to the power of your 8 meter per second part of relation. This already I did it in the dual nature part of relation. And the mass of your electron is how much beta? Mass of your electron is 9.1 into 10 to the power of your minus 31 kg, and is equivalent to how much for me? And this equivalent is given for me, that is nothing but mass of your electron me into your c square. If I'm writing this one is 510 point approximately 99 kilo electron volt. That means 1 UV is mass of your electron will be equal to how much beta? So mass of your electron, if I am writing, mass of your electron is equals to 51.99 kilo electron volt divided by your c square. So 1 atomic mass unit is equals to 1.66 into 10 to the power of minus 27 kg, that is equals to your 931 MeV divided by your c square, So this is your atomic mass unit relation, very important relation beta. One atomic mass unit is 1.66 into 10 to the power of minus 27 kg, that is equals to your 931 MeV divided by your c square part of the relation. Okay. Next one is nuclear binding energy. Nuclear binding energy. Nuclear binding energy. అంటే న్యూక్లియస్ ని బైండ్ చేసే ఎనర్జీ అవుతున్నాయో దాని గురించి మాట్లాడుతున్నాం. దట్ ఎనర్జీస్ ఆర్ కాల్డ్ యాజ్ ఆఫ్ యువర్ న్యూక్లియర్ బైండింగ్ ఎనర్జీ. లైక్ ప్రోటాన్ అండ్ న్యూట్రాన్ ఆర్ కంబైన్డ్ ఉన్నాయి, దాంట్లో ఇంకా సబ్-అటామిక్ క్వాక్ పార్టికల్స్ ఉన్నాయి. దానిని బైండ్ చేసే ఎనర్జీస్ ని మనం మాట్లాడుతున్నాం ఇప్పుడు. ద ఫస్ట్ వన్ ఈజ్ అబౌట్ యువర్ న్యూక్లియర్ బైండింగ్ ఎనర్జీ. ఇన్ దిస్ వన్ ఫస్ట్ we talk about your mass defect. We talk about your mass defect. So what do you mean by mass defect, beta? See, the mass of the nucleus is much smaller than the total mass of the constituents. అంటే mass of electron, proton, neutron అన్ని కలిపితే మనకు ఒక atom అవుతుంది కదా. So the mass of your nucleus, the mass of nucleus, mass of nucleus is smaller than the total mass, is smaller than the total mass of its constituents, అంటే ప్రోటాన్ అండ్ న్యూట్రాన్ గనక క్లబ్ చేసే అయితే మాస్ వస్తుందో ఆ మాస్ ఆఫ్ ప్రోటాన్ కన్నా మాస్ ఆఫ్ న్యూట్రాన్ కన్నా తక్కువ. ఎందుకని? డ్యూరింగ్ బైండింగ్ సర్టన్ ఎనర్జీ హస్ బీన్ లాస్ట్. అందుకోసం ద మాస్ ఆఫ్ ద న్యూక్లియస్ ఈజ్ స్మాలర్ దాన్ ద టోటల్ మాస్ ఆఫ్ ఇట్స్ యువర్ కాన్స్టిట్యూయెంట్స్ పార్ట్ ఆఫ్ రిలేషన్. అంటే మాస్ అండ్ ప్రోటాన్ గనక క్లబ్ చేస్తే నాకు ఒకవేళ 10 రావాలంటే, కానీ 10 బదులు అది ఎంత వస్తుంది? మేబీ 9 ఆర్ మేబీ 8.5. రెండు క్లబ్ చేస్తే టోటల్ మాస్ ఏమవ్వాలా? ఇండివిజువల్ దానికంటే పెద్దది కావాలా. కానీ ద మాస్ ఆఫ్ ద న్యూక్లియస్ ఇస్ స్మాలర్ దాన్ ద total mass of your constituent nucleus. So the difference in the mass of this nucleus and its constituent, we are calling it as of your mass defect beta right now. So the difference in mass of a nucleus, the difference in mass of a nucleus and its constituents delta m is called the mass defect. Okay, so I can write the formula for this one as mass defect delta m will be equal to Z into mass of your protons plus N into mass of your neutrons minus mass of your nucleus. M into this one is Z and this one is your E. So this is your mass defect. So mass defect is delta M is equals to your Z into your mass of proton plus N into your mass of neutron. This is a constituent minus your mass of your nucleus will be giving you the mass defect here. So what is a capital M beta? Capital M is nothing but your mass of nucleus. Mass of your nucleus. Next one is binding energy. Next one is your binding energy. It is represented by EB, or we also write it as of your binding energy BE, anything. See, what do you mean by binding energy is nothing but the total rest mass of the separated nucleons is greater than the rest energy of your nucleus part. అవునా కదా? దట్ మీన్స్ మనం దీన్ని ఇండివిజువల్ గా తీసుకుంటే the total rest energy of separated nucleons is greater than the rest energy of your total nucleus. So the energy delta m into c square that must be added to separate the nucleons is called as of your binding energy part of relation. అంటే extra energy మనం ఏదైతే ఇస్తున్నాము, ఓకేనా? So I can say here right now, the total rest energy, the total rest energy, the total rest energy of the separated nucleons, of the separated nucleons is greater than the rest energy of nucleus, the rest energy of nucleus. So the energy delta m into c square, mass defect into your c square, that must be added that must be added to separate the nucleons, is called the binding energy, that is EB. Okay, so binding energy EB will be equal to delta m into c square. ఆ డిఫెక్ట్ నుంచి మాస్ తీయడానికి ఏదైతే ఎనర్జీ యూస్ చేస్తామో దట్ ఈస్ కాల్డ్ యాజ్ ఆఫ్ యువర్ binding energy, that is delta EB is equals to delta m into your c square. Delta m already I know it, that I can simplify here. If certain number of neutrons and protons are brought together better to form a nucleus, a certain charge and mass and energy will be released in that one. That energy released is nothing but of your this binding energy. So that you need to add this much of amount of energy to bind them. So EB is equals to how much for me? Delta m into your c square part of the relation. That means I can even write this one as of your binding energy EB is also equal to your delta m value రాస్తున్నాం కాబట్టి Z into mass of your proton plus of your N into your mass of your neutron minus of your mass of your nucleus, that is nothing but m into Z into your A into your c square, So you can also use the atomic masses better in the place of your nuclear masses part of relation. So this will be the basic formula for me. Binding energy is equals to your delta m into your c square part of relation. Okay. We can also use atomic masses. In place of nuclear masses. Like binding energy, if I'm writing EB is equals to your Z into your m into this one is 1h1 plus n into your mass of your neutron minus m into, so this is your x, this is number of your neutron n, and this one is nothing but of your n plus of your z into your c square. ఇట్లా కూడా రాసుకోవచ్చు. See, in this equation, mass of electrons cancels out beta. That means there are z electrons in z hydrogen atom as well as of your this one is nothing but of your x into your z. Correct ration anything. Z into mass, this is mass of neutrons. This will be equal to n plus of your z, atomic number of neutrons plus. It is z kada, sorry. Take one small question on nuclear physics, beta. See here. If a nucleus splits into two lighter nuclei with mass numbers A1 and A2, then according to law of conservation of momentum, law of conservation of your linear momentum, the two lighter nuclei move in opposite direction. With equal momenta. Then the ratio of their kinetic energies are ఓకే. చూడండి ఇక్కడ మన దగ్గర ఒక న్యూక్లియస్ ఉంది which is at your rest and it is breaking down into two parts beta. One part of this m1 is moving with velocity v1 and another one of your m2 is moving with a velocity of v2. This is m1 and this one is m2. Momentum conserve అవుతుంది కాబట్టి m1 v1 will be equal to m2 into v2 in opposite direction. అంటే v1 by your v2 will be equal to your m2 by your m1. m2 by m1 is nothing but mass numbers kada, a2 by your a1. So can I write the mass number in terms of your radius beta? R is equals to r0 get cancelled, so it is r2 cube divided by your r1 cube ante kada, because a is equals to your how much for me, r is equals to your r0. We know this relation, r is equals to r0 a to the power of 1 by 3. Relation between this one is how much for me? So a1 by a2 by a1 can be written as of your r2 cube by your r1 cube. That means kinetic energy, if I am writing kinetic energy of the first body divided by kinetic energy of the second body is equals to your m2 by your m1 ante kada. Velocities of that one we got the given condition. So if I am writing the given condition, half into your m into your v square. So kinetic energy will be depending upon what beta? They are moving in the opposite direction with your equal momentum part of relation. So equal momentum ante kinetic energy is inversely proportional to masses kada. Endukani kinetic energy is equals to p square divided by 2 into your m. So momentum same kabatti kinetic energy is inversely proportional to your mass. And this will be equal to your how much for me? This will be equal to your a2 by your a1. a2 by your a1 అంటే ఏం రాయొచ్చు నేను r2 by your r1 to the power of your 3. So this is the ratio of your kinetic energy 1 divided by your kinetic energy of your 2. Okay, so this will be the answer for this question. So the ratio of the kinetic energies will be equal to your how much for me, your r2 by your r1 to the power of your 3 part of relation. Very important question beta. మీ మెటీరియల్ కూడా చాలా క్వశ్చన్స్ ఉంటాయి దీనిపైన. So you can just think of that one and try to do for the given conditions right now. Okay na? So binding energy మనము EB is equals to this one. You know how to write the number of your neutrons beta. So how do you write the number of neutrons here? N will be equal to your A minus of your Z. A minus of your Z part of relation. So this one is nothing but of your M into Z atomic number lo raskochu. This is nothing but of your Z and this one is nothing but of your A. A value is nothing but of your Z plus of your 2. And this unit is nothing but of your joules beta. Binding energy, this unit is nothing but in terms of your joules. In terms of electron volts రాయాలంటే binding energy will be equal to your delta M into 931 MeV. ఇక్కడ రాసుకోవచ్చు నేను. Binding energy will be equal to your EB will also be equal to your delta M into 931 point something basically. So you can directly take 931 MeV. If I'm writing in terms of your model that mega electron volt, then multiply the mass defect with your 931. That will give me the answer for the given condition. Okay, c square value రాస్తున్నాను అంతే. అవునా కదా, c square value ఆల్రెడీ మనకి ఇక్కడ వచ్చింది కదా. ఇక్కడ ఎంత వచ్చింది చూడు, one atomic mass unit is equal to 931 MeV part of relation. అంటే c square will be equal to your how much for me? C square is equal to your 931 into your MeV part of relation. ఆ వాల్యూ రాసుకున్నాను ఇక్కడ ఇండైరెక్ట్ గా బేసికల్. ఓకేనా. The next one is binding energy per nucleon. Binding energy per nucleon. Binding energy per your nucleon. So binding energy per nucleon is nothing but beta the average energy, the average energy required to release a nucleon from the nucleus is called binding energy per nucleon. Binding energy per nucleon. So I can write here binding energy per nucleon is equals to total binding energy divided by mass number. Mass number is nothing but of your total number of your nucleons. Total number of nucleons. That is binding energy per nucleon is equals to EB divided by your E. This is your binding energy per your nucleon formula. Okay, that means binding energy per nucleon is directly proportional to what? Stability of your nucleus. I can say that binding energy per your nucleon is directly proportional to your stability of nucleus. Stability of your nucleus. Binding energy per nucleon is directly proportional to your stability of your nucleus part of relation. Okay na. Tell me the answer for this one, beta. What is the ratio of kilowatt hour and mega electron volt? One kilowatt hour is how much, beta? 1 kilowatt hour is equals to 1 kilo is 10 to the power of 3. 1 watt means 1 joule per second, isn't it? And 1 hour is equals to 60 into 60. So that will be equal to how much for me? 60 into 60. This is nothing but of your seconds, isn't it? So this will be equal to your how much for me? This is approximately 3.6 into 10 to the power of 6 joules. Okay, the same way 1 mega electron volt will be equal to 10 to the power of 6 electron volt. Mega is 10 to the power of 6. That is equals to 10 to the power of 6 into 1 electron volt is 1.6 into 10 to the power of minus 19 joules. So that will be equal to 1.6 into 10 to the power of minus 13 joules. So if I'm taking the ratio 1 kilowatt hour divided by your 1 mega electron volt is equals to 3.6 into 10 to the power of 6 divided by 1.6 into 10 to the power of minus 13. So if we simplify it, this is approximately 2.25 into 10 to the power of 19. So this is the ratio. Okay. Same. See this question better. Find the energy release. Find the energy released if two hydrogen atoms, one H2 nuclei can fuse together to form 2He4 nucleus. Okay, the binding energy per nucleon of 1H2 and 2He4 is 1.1 MeV and 7.0 MeV respectively. Tell me. So what is energy released? What is happening right now? If 1H2, that means 1H2 plus 1H2, both of them are reacting. So what will be getting better? 2 and 2, that means second element, helium, and mass number will be 4. Along with this one, certain amount of energy is released. So binding energy of this one is given how much for me? So this one is nothing but 2 into దీనికి ఎంత ఉంది right now for me? So the energy released to hydrogen atoms confused to form in helium nucleus. The binding energy per nucleon of 1H2 and 2He4 is 1.1 MeV. That means this one is 2 into 1.1 plus this one is 2 into 1.1. That will be equal to 4 into the binding energy and the 7.0 plus certain amount of your energy is been released in this one. See then this one is nothing but 2.2 plus this one is 2.2. This one is giving you right now. ఇది ఎంత అవుతుందన్న 28 plus certain amount of energy. అవునా కదా? So E will be equal to how much for me? 28 minus 4.4. So that is approximately 23.6 MeV. So this much amount of energy is being released. Okay, na? ఇంకో క్వశ్చన్ చూసుకున్నాను. Compute the energy equivalent of 1 gram in kilowatt hour. Okay, so 1 gram is how much, beta? 10 to the power of minus 3 kg. And C is 3 into 10 to the power of 8 meter per second. So E is equals to your M into your C square. So that is equals to 10 to the power of minus 3 into 3 into 10 to the power of your 8 whole square. So that will be equal to 9 into 10 to the power of your 13. 9 into 10 to the power of 13 joules energy. So 1 kilowatt hour will be equal to, this will be equal to how much for me beta? 1 kilowatt hour is equals to 36 into 10 to the power of 5 joules. ఇంతకు ముందే చెప్పాను నేను ఇక్కడ. So 1 kilowatt hour is 3.6 into 10 to the power of 6 joules or 3.30, nothing but of your 36 into 10 to the power of 5 joules రాసుకోవచ్చు. So 31 kilowatt is equals to how much for me? 1 kilowatt hour is 36 into 10 to the power of 5 joules. Okay, that means 1 joule will be equal to how much beta? 1 joule will be equal to 1 kilowatt hour divided by 36 into 10 to the power of 5. So therefore I can say that energy equivalence of 1 gram is equals to 9 into 10 to the power of 13 joules. 1 joule is equals to 1 kilowatt hour divided by your 36 into 10 to the power of 5. So if we simplify this one, this will be getting 2.5 into 10 to the power of 7 kilowatt hour. Okay. Next one is nuclear energy. Nuclear energy. బైండింగ్ ఎనర్జీ కర్వ్ ఒకటి ఉందని అన్న, అది ఒకసారి మీరు ఎన్సీఆర్టీ నుంచి తీసి చదవండి అన్న కర్వ్ పార్ట్ ఆఫ్ రిలేషన్. సో వాట్ యు మీన్ బై యువర్ nuclear energy? So the energy of nucleus, it is nothing but simply, it is the energy of nucleus. It is the energy of your nucleus. Energy of a nucleus. That means when nuclei with less binding energy transforms into nuclei with greater binding energy, nuclear energy has been released. So there are two fundamental processes to consider beta while taking out the nuclear energy. One is nuclear fission, another is nothing but nuclear fusion part of relation. So I'll write that points right now. When nuclei with less total binding energy, transform to nuclei with greater binding energy, comma, nuclear energy is released. Okay, so there are two fundamental processes. Okay, there are two fundamental processes which are being considered for taking out nuclear energy. First one is nuclear fusion. First one is your nuclear fission. Next one is nuclear fusion. Next one is your nuclear fusion. Okay, so we'll try to do this one in detail in the further section. Let us try to first write how do you write a nuclear reaction. How do you write a nuclear reaction? నాకంటే మీకు బెటర్గా ఐడియా ఉండాలా, because in chemistry you might have been got an idea how to write your nuclear reactions part of relation. See, in the nuclear reaction, what exactly is happening is the process by which the identity of a nucleus is being changed. when it is been bombarded with any energetic particle, they are called as of your nuclear reactions part of relations. I can write here right now the process by which the identity of a nucleus is changed when it is bombarded by an energetic particle energetic particle is called nuclear reaction. Is called what? Nuclear reaction. General expression, if I'm talking about, general expression. So if I'm talking about the general expression, so ఏమవుతుందంటే ఇక్కడ first one is say for example this is your X, which is known as of your parent nucleus, is being attached with added with your incident particle. An incident particle is attached on the parent nucleus. So during the reaction, it will give you a product which is known as of your C. C is nothing but of your compound nucleus which has been formed. This compound nucleus will give you the result. That is nothing but a product in nucleus is being formed. Along with that one, a daughter nucleus is being formed. And along with that one, certain amount of energy is being released. I'll write in the down here right now. X is nothing but parent nucleus. X is nothing but what? Parent nucleus. And A is nothing but of your incident particle. This one is your incident particle. When any incident particle is incident on the parent nucleus, so we get a compound nucleus. C is nothing but what for me? Your compound nucleus, which will give me the Y. Y is nothing but product nucleus. Y is nothing but of your product nucleus. And B is nothing but of your daughter nucleus. B is nothing but of your daughter nucleus. And Q is nothing but of your energy released. Q is nothing but of your energy released. So this is a way how do we write the total equation for this part of relation. Okay, so this is your nucleus reaction. So general expression is X plus A. When a parent nucleus is being incident with a particle, we found a compound nucleus. That compound nucleus will give you the product nucleus. We will be getting a product nucleus. Along with that one, a daughter nucleus has been formed. Along with that one, certain energy is also been released in the given process part of relation. Clear? See. Conservation laws obeyed by the nuclear reactions. Conservation laws obeyed by nuclear reactions. Obeyed by your nuclear reactions. ఇది కంపల్సరీ గుర్తుపెట్టుకోవాలి నాన్న. This is the backbone for your nuclear reactions phenomenon. The first point is mass number and electric charge is conserved. Okay, so that is Z sum of all the initial atomic numbers must be equal to sum of all your Z final, and sum of your all initial mass numbers must be equal to summation of your all the final. Okay, that is the first point. Second point, linear and angular momentum are conserved. Beta. Linear and angular momentum are conserved. This is the second form. And third one is total energy of reaction. Total energy of reaction remains conserved. Total energy of the reaction remains conserved in terms of Q to balance the total energy of your reaction. Okay, in terms of your Q. So that are some of the conservation laws which you need to remember for the given conditions part of relation. And how do you write the Q values? We'll try to do it out for. So initial atomic number must be equal to final atomic number, and initial mass must be equal to sum of your final masses basically. Okay. Next one is Q value. Q value ante energy. Equation lo idi rasham kada EQ value ela calculate chestunam. So Q value is calculated. So here see here Q value means the difference between the rest mass energy of initial constituents and the rest mass energy of final constituents of a nuclear reaction. Okay, so if I'm writing the Q value of a nuclear reaction, beta, Q value of nuclear reaction ila rastanam chudandi. If X plus A are being reacted to give you Y plus B plus of your Q, then Q will be equal to initial energy minus of your final energy. So what is UI? UI is your rest mass of, this is your rest mass of initial constituents. And what is U final? U final is nothing but rest mass of final constituents. Okay, so if I'm writing this one, this is your Q value for the given reaction. So whatever the reactions we are taking right now for this Q reactions part of relation, so QI is your initial part and this one is your given condition. So this is the way how do we calculate the value of your Q. Okay, so let me write the Q value more detailedly. So Q value will be equal to mass of your X plus mass of your A minus mass of your Y minus mass of your B. I have removed the bracket better. into your C square, into your C square. Okay. So delta Q is equals to delta M into your C square part of a relation. So that is a relation. How do we write the value of your Q? So Q is equals to mx plus of your mb minus my minus mb. Okay, my minus mass of your daughter nucleus, which has been the mass of your product which has been formed, minus mass of your daughter nucleus into your C square part of relation. If Q value is coming out to be positive beta, if Q is equals to positive, then reaction is exothermic. Antena? Reaction is exothermic. If Q value is coming out to be negative, then reaction is endothermic. Reaction is endothermic. Okay. So Q ఎలా రాసినాను ఇక్కడ? So from the relation Q is equals to delta M into C square, our energy E is equals to delta M into C square part of the relation. Next heading beta, nuclear forces. Okay. See, if I'm talking about the force of attraction, between nucleus in nature, మనకు నేచర్ లో ఉన్న ఫోర్సెస్ లో force of your nuclear is greater than force of your electrostatic. షేర్ అవుతుందన్న? Nuclear force is greater than electrostatic force, and electrostatic force is greater than of your gravity beta. But nuclear forces are independent of your charge. In nature, if I'm taking right now, nuclear forces are independent of your charge beta. Nuclear forces are independent of charge. Are independent of your charge. Are independent of your charge particle relation. If they are independent, means the nuclear force between two protons is same as that of your protons and as well as of your neutrons particle relation. Only for nuclear forces I can say that force between proton will be equal to force between proton neutron, and that is also between force between neutron and neutron, because it is independent of your charges. So if I'm talking about the relation right now, if F1 is the net force between two protons and F2 is the net force between your proton and neutron, and F3 is the force between neutron and as well as of your neutron. Now what will be the relation between the net forces between the nucleus beta? Like say for example, మన దగ్గర ఒక న్యూక్లియాన్స్ ఉన్నాయి. ఇందులో మన దగ్గర ప్రోటాన్, ఇక్కడ ఒక ప్రోటాన్, ఇక్కడ ఒక న్యూట్రాన్, ఇక్కడ ఒక ప్రోటాన్, మళ్ళీ ఇక్కడ ఒక న్యూట్రాన్ ఉంది. ఓకేనా? see, సో న్యూట్రాన్ ప్రోటాన్ మధ్యలో ఒక ఫోర్స్, ప్రోటాన్ న్యూట్రాన్ మధ్యలో ఒక ఫోర్స్, అండ్ ప్రోటాన్ అండ్ ప్రోటాన్ మధ్యలో ఒక ఫోర్స్, అవునా కదా? అండ్ ప్రోటాన్ అండ్ ప్రోటాన్ మధ్యలో కూడా ఇంకో ఫోర్స్, అంటే there will be your electrostatic force between them. So this is your F electric and this one is also your F electric. Okay, like say if I'm telling you right now, F1 is equals to net force between two protons, and F2 is equals to net force between two proton and neutron, between not two, I can write between proton and neutron, and F3 is equals to net force between neutron and neutron. Then I can write here F1 will be lesser than F2, but this will be equal to your F3. That is the relation between the forces. Okay, so I can say that this is a very important relation now. So force between two protons is lesser than the force between two proton and neutron, but this will be equal to how much for me? Your F3, that is net force between neutron and as well as of your neutron particle relation. So nuclear forces are attractive in nature. Strongest is nuclear, and they are also lowest range. Nuclear forces are of low range right now, that is 1 to 2 Fermi. It is not central forces and spin dependent and charge independent particle relation, that you can check it out from your material particle relation, what all the nuclear forces have been acting on the given condition part. So in almost all stable nucleus, if I am talking about, number of neutrons will be greater than of your number of your protons. In almost all stable nucleus, you can keep a star mark right now. In almost all stable nucleus, number of your neutrons is greater than is greater than number of your protons. Number of protons if size is large. If size is large. If size is large. And very heavy nucleuses are unstable beta. Very heavy nucleuses are unstable. That is the reason they undergoes the process of your radioactivity particulation. So very heavy nucleuses are unstable particulation. Can even keep that point here. Very heavy nucleus are unstable. Very heavy nucleus are unstable. Very heavy nucleus are unstable. That means in heavy nucleus, due to large size, balancing the forces cannot be achieved better, even by extra neutrons due to their size. That is the reason they get split. What is happening is in a heavy nuclei, due to large size, balancing of forces cannot be achieved even by some extra neutrons due to size. Like చూడండి ఇప్పుడు this is your size of your nucleus అనుకుందాం. Okay, so if I'm talking about your one extra nucleus right now here, ఇది దీంట్లో ఏమవుతుంది ఇక్కడ this is one neutron, this is your one neutron, this is one neutron, this is one neutron, and there are some protons, and some protons. Now because of this larger size, what is happening is these neutrons cannot bind them. This proton these neutrons cannot bind. So that is the reason what happens, it splits into your lighter nucleus. So such nuclei spontaneously break. Such nuclei spontaneously break. So they will be breaking apart and or rearrange their internal structure. Their internal structure to achieve relatively stable structure. This phenomenon is called radioactivity. Okay na? So why a nucleus is getting split ante in heavy nucleus lo oka proton ni number of neutrons cannot balance even though they are neutral in the nature. So what happens, in order to get the stability, they will try to break into the smaller elements part and try to get the stability. So that is the reason heavy nucleus will try to split on their own to get a stability. That process of splitting is called as of what? Radioactivity. This process of splitting is called as of what for me? Radioactivity particulation. So then we have something related called as of your binding energy curve right now, that I'll try to do it in the tomorrow session of a class. Today you try to give an introduction study related to your nuclear physics, and the tomorrow will start with your radioactivity, half-life periods and their conversions, alpha, beta, electron capture, beta plus, beta minus decays basically, and we'll try to do even electron capture, radioactivity law, spontaneous relations, their graphs related. Okay, and we'll try to keep the full stop for this topic. It is almost like similar to your chemistry topic only now. Chemistry would I point as most probably, so you can just refer the notes And please try to read this chapter from NCERT only. NCERT material ఉంటే NCERT తీసి ఒకసారి తీసి చదవండి. Sending the material for you.